All right, welcome. So we wrapped up the stuff with the budget constraints, the intertemporal constraints, and all that. And I guess to further confuse you guys as to the course that you're actually taking, because I'm sure a lot of you probably thought, "Hey, I thought I was taking money in banking, and why are we getting all this stuff?" Um, well, I'm going to take that a step further, and we're going to learn about a little time series econometrics. Now, we're not going to learn like how to really do a lot of this stuff because that's honestly outside the scope of the course. I don't think it's the most important thing in the world for you to know how to do this stuff, but I do think it's important for you to be able to interpret some various results. So um, this lecture hopefully isn't going to be too terribly long. I'm going to try to keep it relatively short. And just give you guys the basics of really looking at impulse response functions. So it's like looking at like a graph, essentially. You don't have to interpret any tables with all these numbers and these like different statistics. And you don't have to do any of that stuff. So you're not doing any statistical tests. You're not really doing any statistics. I just need you to tell me, what do these results tell us? And the results are just graphs. They're little pictures. You don't even have to draw the graphs. All you have to do is just look at the picture and tell me, hey, does this work? Does this not work? And we go from there. So, um, I realized I typed a lot of this stuff up, and then was like, I don't know how ultra important it really is for me to have a lot of this stuff here. So I guess if you're really interested and you want to learn about doing this stuff, hey, great, be my guest. But essentially, what we're doing is we're looking at what's known as an autoregressive process. If you've taken statistics and you know what a linear regression is, this is just that. It's a linear regression, only the thing is, most of the regression stuff that you had seen was like it was a cross section. So you're looking at a number of different samples all in one time period, and there's no additional time period for you to see the time series or see the process like evolve through or anything like that. It's just here's a bunch of numbers and you just find a relationship between them. An autoregressive process is a little different. It's where you're looking at the behavior of something over time. So the ordering of your observations matters because you'd have like GDP in Q1 1990, Q2 1990, Q3 1990. You can't change the order of that because then, well, the evolution changes over time. So the ordering matters. And for an autoregressive process, what you're doing is you're saying, okay, well, I have this regression, right? I've got this relationship between two variables. But the two variables that I'm looking at are really just the same variable, but different time periods of that variable. So if you're looking at, say, an AR or an autoregressive one process with one lag, you'd be looking at equation one, say this is GDP. What you're seeing is you're looking at GDP, that Y sub t, that's today's GDP, being a function of last quarter's YT minus 1 GDP. And that's telling me, okay, think of it like inertia, right? There's going to be a little bit of inertia in the process that we're looking at. So if GDP's value was, I don't know, YT minus 1 last quarter, YT is probably going to have something to do with what YT minus 1 was. Depending on where YT minus 1 was, YT is probably going to be fairly close, plus or minus maybe a little bit of error. And that's what equation 1's telling me, right? It's saying today's value for GDP is a function of, we'll get to this A0 in just a second, alpha 1 times YT minus 1. Well, alpha 1's just the relationship, the estimated relationship between last period's value or last quarter's value of GDP and this quarter's value of GDP. And, if you ever do look at something like this, if I ever do give you something to play with, like on a homework or an exam or something, this alpha 1, like you'll get that. I'll tell you what it is. You'll have an actual number here. So that's what this is. It's just think like slope, right? Y equals mx plus b. This is y equals m alpha 1 x yt minus 1, or the independent variable, plus b. This is a naught. This is like, you can think of it like an initial condition. It can be the constant. the y-intercept, if you remember slope-intercept form. So that's what the first two terms on the right-hand side are. It's just telling me, okay, this is where the regression crosses the vertical axis. This is the slope of the regression. This is the independent variable. So what's this ET thing? Well, it's an epsilon. It's not an E. It's an epsilon. And it's an error term. It's the difference. Error is actually kind of a misnomer for this. It's a residual is probably the better thing to call it. But since we're not all time series econometricians here, maybe just calling it an error would make a little bit more sense. It's the difference between what gets observed and what gets estimated. So, we'll observe YT, but then we can also estimate YT because we know what A naught and or alpha naught and alpha 1 are. So it'll give us an estimate for Y sub t, and we can compare the estimate against the true or the observed value. And that difference between the estimate and the observed value is the residual or the error term. So that alpha 1 term, it's this parameter is called an autoregressive coefficient. It gets estimated via the statistical estimation procedure. What you don't really need to worry about here. If you've taken statistics, then it's ordinary least squares is generally what's used for this stuff. Although there are times where using ordinary least squares is not the best thing. We can use like maximum likelihood or something like that. But that slope tells me the relationship between today's value and yesterday's value. It explains really, it's telling me that past behavior in some way, shape, or form helps predict future behavior. That parameter is assumed to be somewhere between -1 and 1, not inclusive, so it's not equal to -1, nor is it equal to 1. It has to be strictly in between the two in order to be what's known as stationary. And really, to be stationary, it has to have a constant mean and variance. What is a non-stationary time series? This would be non-stationary because you can see it's got this like upward trend to it, right? So if you were to draw okay, well, if I want to draw a straight line here and here, like say from, I think it's like 2008 when this starts to 2010. All right, well, you'd have a mean for this time interval. But then if you look at, say, start at 2010 and 2015, what would the mean there be? Well, the mean would be a little higher. It'd probably be somewhere like around here. But then if you look at 2015 to 2020, where would the mean be? Well, it'd be somewhere like up here. So you can see that, for any time window, the mean isn't going to be the same. It's going to change depending on where you go throughout time. That's not really a good thing. It's not something that we want to have, right? So we could have a stationary time series. You could basically just draw a straight flat line through it, and you would, in all likelihood, have a constant mean. That's basically what a stationary time series is. Again, you're not going to be tested on a stationary time series, whether it's, stationary or not. There's different ways to get a stationary time series. A lot of these you've actually seen before. You can just take a first difference, so like, YT minus 1, or the difference between what today's GDP was and yesterday's or last quarter's GDP was. You can do a percent change that actually generally gives you some stationarity. You can do linear detrending, which I'm not really going to show you how to do that. There's really no point. But if, you do try to get some of those things, you tend to lose a little bit of information in there because you're interpreting the data differently, right? If you're looking at a percent change rather than the level is, well, it's telling you the level. The percent change is telling you like the rate of change or a growth rate. It's still useful information, but it's not useful in the same way that looking at the level would be. That's for just an individual time series, right? Univariate time series. But the thing is, we can actually look at a lot of them together. We can look at more than one time series together. So what I had before, right? All right, equation 1, this was a univariate time series because it's just GDP, right? It's an AR process. So there's multiple values of GDP that are affecting current values of GDP, but it's still just GDP, right? GDP and, last period's GDP. So if you can do that for GDP, well, you can also do that for prices, right? Like Okay, well, now I've got an equation for GDP. Equation 2, this tells me the evolution of GDP over time. And then I've got another one for prices, one that tells me about the evolution of prices over time. And, current price level is a function of the previous terms or previous period's price level. Current output is a function of previous output. I got these two guys together, but they're still evolving like independently of one another. But the thing is, like, we've looked at supply and demand, right? You look at your supply and demand graph, and you've got price on the vertical axis and output on the horizontal axis. So price and output are kind of related to each other, right? There's a relationship between price and output. So if there's a relationship between price and output, then maybe we need to be modeling that. I mean, it makes sense, right? I mean, think like if yesterday's value for output, probably plays a role on what the price is today. If there's supply chain problems over the last couple months, the price is probably going to be reflected. That's probably going to be reflected in the price today. Just makes sense that that's probably what would happen. Maybe takes a month or two, but eventually you'd see it. And so we wouldn't necessarily expect it contemporaneous, like there's a change in output today and prices change today. Probably see like a little bit of a lag. Maybe say they're changing output or production a quarter ago, right? So that's within the last 3 months. You see a change in output. You probably see a change in price. That's a measurable change in price this quarter. So you maybe have a little bit of a lag. So if we got prices here, right, what I had in equation 3 was price just being a function of the last period's price level, which we got right here. But also, what if I had last period's output? Because that might play a role in determining what price is today. So last month's or last quarter's value of output is going to be affecting what price is this month. And if output and price are correlated, it would probably make sense to have this instead of just lags price, because there's valuable information in that variation in output that we're looking at in determining the way that the price level will be evolving over time. But maybe like output would also respond to changes in price, because the price is just a signal, right? If you think about it as a producer, the price is a signal whether you want to produce more or less, right? So if the price level goes up, just say price for a particular good or service that you provide goes up, you're like, hey, cool, I can make more. I can earn a little bit more profit. I can increase my profit if I produce more of this stuff. But then you produce more of the stuff, the output goes up, and then prices fall because you have more supply. So there's a relationship between output and price. And there's a relationship between price and output. So just like I had that specification for prices in equation 4 where I had lagged output in there, there's a good reason for why you might want to have lagged output in there. There's also a good reason for why you might want to have an equation for output with a lag of price in here. So I put the lag of the price level in here. So we got previous values of the price affecting current values of output. And I can get more information out of that because nothing really evolves in a vacuum. Nothing evolves independently of everything else, right? There's always something kind of affecting other things, and those other things affect other things, and they're affected by things and all that, right? So in this case, price affects output, output affects price. And you got like demand and you have supply. There are relationships in both the demand function and the supply function between output and price. So here's what's kind of a problem at first, right? If output and price were exogenous, we could then make an argument that, say, output would affect price, but price doesn't affect output. We would know what the direction of causality would be, right? One thing is causing this, but this one thing, X causes Y, Y doesn't cause X. But That's nice. It's like going, okay, well, we've got the chicken and the egg, and we know the egg always comes first. But with output and price, it's not that simple because the egg doesn't always come first. The chicken lays the egg, right? The egg doesn't come out of a vacuum. The chicken lays the egg. So for output and price, that causal direction sort of goes both ways. Like there's a relationship between each of them. If output increases, prices fall. If prices increase, you might want to produce more stuff, right? I mean, that makes sense. If you're a producer, if the price goes up, you want to make more stuff. Okay. So what? Well, if I model these two equations separately, then we don't really have a reliable estimate of those those alpha terms, right? Because these variables are endogenous. So the question becomes, can we do anything to fix this? And the answer is yes, because we can model them just together. What we can do is we can have a vector autoregression model. And what you're like, oh God, what the hell is that? Or VAR. Well, it's where I just take the specifications, right? I take equation 4 for price and equation 5 for output, and I estimate them simultaneously. That's all I do. And this thing looks like what you see in equation 6 and 7. It's a system of equations, right? If you remember systems of equations in algebra 2, that's equation 6 and 7. It's just a system of equations. And the thing is, right, I've got what's in blue. These are the lags of output affecting output, or the lag of price affecting price, right? So in equation 6, I've got yt and yt minus 1. Yt minus 1's in blue. Equation 7, I've got pt and pt minus 1. The pt minus 1's in blue. All right, so these are like the individual output and output, price and price thing. But you also get these cross terms. They give me the cross covariances between output and price. So now what's in pink in equation 6, that's the previous value of price. Well, the previous value of price can be determined by looking at what the previous value of price was, say, for equation 7. And the previous value of output, we can get that by looking at the previous value of output in equation 6. So you change one, now you're changing the other. And you're not changing the other kind of like going, well, this changes and then I'll take this and plug this. No, you change one, it immediately and directly changes the other. So they're functions of each other now. And because they're functions of each other, when you change one, you will invariably be changing the other, which is consistent with what you would see for like supply and demand. And where I said it was a problem initially, right, that endogeneity problem, where I said it existed initially, it's not really so much a problem. It's actually kind of a benefit to us when it comes to this, because we can take advantage of that. We can take advantage of the endogeneity between these two variables by having the system of equations. And with that system, I can impose a shock to one equation and see how the other would be responding to it. So if I have a shock to output, I can see how prices respond. And with this, we're modeling supply and demand. Now, the thing is, I've got two equations. And if I've got two equations, right, remember if you've got in algebra 2, you have a system of equations. If you've got two equations and two unknowns, you can solve uniquely for those two unknowns. Think of it the same way here, just in terms of like shocks. If I've got two equations, I've got two sources of shocks. Now, where are the shocks going to be coming from? Well, the shocks come from these residual terms, the epsilon y and the epsilon p. Right? This is the difference between what gets measured and what gets observed and what gets estimated for output. This is the difference between what gets observed and what gets estimated for price. So we can think of these being sources of information coming in from like outside the model, right? Because, well, everything here is determined, like once we estimate what the alphas are, well, that's kind of it, right? Like that's the deterministic component. We know what that is. We know what it's going to be. The stochastic component, right? That's this thing right here. That's like the wild card. That's the thing that we're like, what's if you're going to have any surprises, any shocks to your system, it's going to enter through this guy for output and this guy for price. So if we impose shocks, I've got two equations. I have two sources of shocks. One to the output equation, one to the price equation. So we've got these two shocks. Now the question is, how can we be sure if we increase output, we only get one of those two shocks? Because if output and price are correlated with each other, there's useful information to extract from that. It may not be that much of a stretch to assume if output and price are correlated, maybe those residual terms themselves are correlated, because like where output, this is, a stream of data, and this is a stream of data that we, observe and plug into the model. And for each individual point that we are estimating, well, that gives me an estimated value, and I have the corresponding observed value, and the difference between that is this residual. So if I've got a stream of data here, I've got a stream of data here as well. So this stream of data could be correlated with this stream of data. And if they're correlated with each other, well, might have a little bit of an issue, because if I'm trying to find a shock to one of them, I could get elements of a shock from the other. Think of it like supply and demand. Well, if elements of a supply shock are correlated with elements of a demand shock, you might get some of the behavior from a demand shock inside a supply shock. So you need to make sure that you're identifying the shocks appropriately. And here's a nice little example of this, right? So we all know that I love NyQuil. NyQuil is amazing. Say I want to look at a demand and a supply shock of NyQuil over time. Well, this is the VAR that I estimated a few slides back, Y being the quantity of NyQuil and P being the price of NyQuil. And I can have a little bit of an idea here about how supply and demand shocks would be working. For a demand shock, if you hold the supply curve like fixed, well, output and price would be moving in the same direction, right? Because if you just draw a demand shock along that upward sloping supply, well, if the demand shock goes outward and supply is upward sloping, then you have an increase. The equilibrium output and price would be increasing. For a supply shock, well, you're holding that downward sloping demand curve fixed, and output and price would thus be moving in opposite directions if supply increases. So for a demand shock, if we go from D1 here up to D2 here, holding this upward sloping supply curve fixed, well, the demand curve shifts out along this upward sloping supply curve, so the new equilibrium output and price would be increasing. So, in general, for a demand shock, if you see a shock where output and price move in the same direction, that's probably a demand shock. Conversely, a supply shock, output and price move in opposite directions. So if there's an increase in the supply of something, well, output goes up, but because there's more of that stuff in supply, it's, less... There's more of that good, right? More people can get those things. So if price is a rationing mechanism, which it is, and you get more of something, well, you don't have to ration it as much. You can have a lower price. So you have a lower price with that increase in supply. So if we know a little bit of economic theory on what supply and demand shocks are like, you can use it when you're trying to identify shocks here. And the idea is that you want to be able to look at these responses over time, where output and price, say, move in the same direction, then you're looking at a demand shock. If you're looking at responses over time where output and price move in opposite directions, it's got to be a supply shock. And the notion is that, okay, let's say we've got the stationary time series, and it's kind of just moving along in a steady state, or it's like going along like a flat line. It's just, it's not going up, it's not going down. It's just moving along a flat line over time. And then at, say, t sub 0, the shock hits, and the time series will jump up or down, depending on the direction that we expect it should be responding. So the graph would start at, say, t sub 0. So we're not looking at when it's moving along that flat line before the shock hits. We're looking right, boom, when the shock hits. And then we look at what happens after. So there's nothing before the shock hitting that we're looking at. Now, the response to this shock that we're trying to see here is what's known as an impulse response function. And it shows how a variable responds to a shock in, say, another. So if I have a demand shock, well, I've got the price of NyQuil and the quantity of NyQuil here. The price of NyQuil, let's look at that first. Well, so we know that like demand shocks, output and price move together. They move in the same direction. Okay, so at t0, right, the little mouse is right here at 0. At this point here, this is when the shock hits. When the shock hits, whoop, it jumps and it increases for a little bit, and then it kind of falls a little bit. Maybe it levels off, something like that. But overall, if you had to look at this, see the price of NyQuil, and you had to say, okay, did the price of NyQuil go up or did it go down? And you'd say, it went up. It unambiguously went up. Because, well, this is 0, right? Look along the vertical axis, this percent deviation from like a steady state. Well, this is, for the mouse right here is at 0, then this is above 0, right? Look at the vertical axis, 0.01, 0.02, 0.03. Well, these are obviously positive values. So it increases. Okay, let's look at the quantity of NyQuil. What did that do? Well, that also increased. And if it's a demand shock, you expect it to be a demand shock. If the price goes up, the quantity should also go up. Oops. So again, we're at t equals 0 and whoop, jumps up. It increases. So you have an increase in both the price and the quantity of NyQuil. Let's look at the supply shock on the other hand. Well, we'll start with the quantity here. The quantity goes up, right? Because again, now here we've got like this nice solid black line. That's that's when the quantity or the percent deviation from the quantity is 0. All right, well, this is clearly above that. So quantity goes up. How much does it increase by? Well, 0.003%. So it's not like a huge increase, but it's a little bit of an increase, right? So it increases here. Quantity of NyQuil is above 0. So if the quantity of NyQuil is above 0 for a supply shock, all right, remember supply, the quantity increases, the price should be expected to decrease, and that's exactly what happens here. Look, right, negative 0.0015. The price at t equals 0, which is where this little mouse is right here, it drops. Okay, and then it kind of increases and sort of goes back to like, it sort of levels off. But, right, we're interested in this kind of stuff right here. What did it generally do? Is it above or is it below 0? Well, here it's below 0. The percent deviation, the price fell below it where it was in the steady state. So if, say, the price here is, say, $2, okay, well, it would be, the price would fall by $0.00015, right? Or 0.015 cents, something like that. So the price doesn't fall by a lot, but it still falls. The quantity increases. So that horizontal axis that we're looking at, right, that's time. See, months. That's unit of time, months. The vertical axis is the magnitude by which the variable responds over time. And it varies depending on the units that variable is expressed in. It's typically percent deviations for stuff like output, price, monetary aggregates, things like that. But if we're looking at, say, an interest rate, well, that could be basis points. And the thing is, we want to look at the maximum deviation when we're looking at these responses. So you want to look at the peak or the trough of the variable's response. And that's going to tell you how it responds to a shock. So I don't care so much about the slope of these things. So like, it's like, okay, well, this it's really steep here, and then it levels off, and then it gets a little steeper, but as we go through time, it kind of levels, and the slope is a little flatter. Or here, it's a really steep increase, and then we don't care about that. I care about what the maximum deviation is. So here, the maximum deviation is what, 0.0001, probably 4% or something like that. And then here, the maximum deviation is probably 0.0035%, because that's the peak, right? This is the peak here. This is the peak here. Well, wait a minute. Hold on a second. You're probably going, if this is the the maximum response, and this is the maximum response, we're looking at the thing in green. So what's all this purple stuff? Well, this purple stuff is, if you remember your statistics, if you've taken it, if you remember like your confidence intervals, think of it like that. It's, in this case, for this particular interpretation, it's 68% of the draws for the solid line, this dark purple area right here. It's 68% of all the draws I get, or 68% of the distribution. The dotted line, that's, I believe, 95% of all the draws. So it tells me how reasonably certain I can be that what I'm getting for this green thing is the median draw, the middle draw. So it's telling me how reasonably certain I can be that this median draw is, well, in this case, negative or below where the price level was. And in this case, it's above where the price level was. Now, if these bands, the tighter these bands get, or the smaller these bands get, the more reasonably certain we can be that, the median is doing what it's doing. But really, all I want you to do is I want you to look at this and tell me, does it go up or does it go down? Now, there are some exceptions, but generally just interpret it as it increases or it decreases. It increases by X amount. It decreases by X amount. So those blue bands, right, which I was talking about, these confidence bands, tells me about 68% of the draws fall within those bands. So if these bands are above or below 0, and what I mean is, say, for this response in quantity of NyQuil, right, these bands, let's just look at the solid bands here. Don't look at the dotted line. Just look at the solid, right? Well, this green line increases. It's above 0. So if that's the case, if this green line, the median draw, is above 0, well, the upper bound on these draws will obviously be above 0 because it's going to be above where this green band is, but the lower is what would be important here. Is this lower band still above 0? The answer is yes. Because while the lower band, the peak, I guess, of the lower band here, where the median draw peaks, it's what, 0.002% above 0. And well, this is 0, so there's a vertical distance between this upper, or this lower band, and 0. So at some point, I can be fairly certain that there's a statistically significant increase in the quantity of NyQuil. Now, as I get over here, say 25 months, well, at 25 months, you can see that this lower band starts going below 0. At that point, right, by this point here, if the lower band is below 0 and the upper band is above 0, well, that means I've got draws that exist within my 68% of like the distribution of draws that I have. I've got some draws that are above 0 and I've got some draws that are below 0. So I can't really be as sure anymore if the draws that I'm getting are all above 0, because some of them are below 0 and more of them are above 0, but some of them, a good amount of them, are below 0. You can't really be as certain anymore as you could, say, over here. So if I've got an increase and the lower band is above 0, it's significant. If I've got a decrease in that variable and the upper band is below 0, it's a significant effect. So the price of NyQuil in the supply shock example, these upper set of bands were below 0 for the first 10 months. Right here. So if you look at the dotted lines, it's about the first 10 months. If I look at the solid line, it's within the first 15 months. Right? Because if I'm looking at the 68%, well, it's 68% of my draws. Playing a little bit more loosey-goosey than if you're, say, looking at 95% of the draws. 95% of the draws, okay, well, that's 95%. This is 68%. But typically for what we're looking at, it's usually 68%. Now, the thing is, if the response is negative, the upper band must be below 0 for there to be a significant response. If the response is positive, the lower band has to be above 0 for a significant response. If that upper band is above 0, the lower band is below 0, the response is not significant and I can't say anything about it. So if I can't say anything about it, what does that imply for how I need to be interpreting where that median draw needs to be? Well, it's no longer significantly different from 0. Therefore, I can't say anything other than it might be 0. So at that point, it's like a 0 change, a 0 response. I can't say anything about it, right? So why do I care about this? Now, I care because I can model an entire economy using this technique. And now it's not going to be like the entire economy, like every single variable in the economy, because, well, that would be insane. It can be every single relevant variable in the macroeconomy: GDP, inflation, a monetary aggregate, and say an interest rate on the money. Then all these variables are endogenous with each other. You can't model one without modeling the others, so you can just model them all together. And now you've got 1, 2, 3, 4 equations. You can have 1, 2, 3, 4 shocks. Now, there'd be one shock in particular. If I'm looking at these 4 variables, there's one shock in particular that I would be very interested in, and that would be a money supply shock. And I can look at how output and prices would be responding to a shock in monetary policy. And that'll give me an idea as to how the entire economy responds to these shocks based on the observed and estimated relationships between them. And then we can start to ask ourselves what policy, if really any, would be appropriate for the central bank to take in the event that, say, we go into another recession. So I'm going to do a little example, and we can look at how we interpret it. So say we've got an economy with real GDP, core PCE prices, the money base, and the 10-year Treasury yield. And I'm using data from October 2008 to February 2020. I'm using data starting in October 2008 because that is when the financial crisis hit. I don't really want to use anything before the financial crisis because the monetary policy regime changed. So with that regime change, you don't really want to, that huge shift, you don't want to have stuff before the shift and stuff after the shift, right? You want to use relevant data here. And it goes up to February 2020 because we all know what happened in March of 2020. Again, a big regime shift. We don't want to have that in there. And I get monthly data from the Federal Reserve Economic Database and macro advisors. And I want to model shocks to this model economy. So there's 4 variables. I can identify 4 shocks. But like I said earlier, I'm only interested in one right now. It's a monetary policy shock. So what I'm doing is I'm just saying, okay, I want all these, I'm going to impose a bunch of shocks, and then I'm going to draw the shocks that match this combination of signs that I'm interested in. So what signed responses would I be interested in? Well, the economic theory tells me there's a certain combination of signs for these responses that would be consistent with a monetary policy shock. What would they be? Well, we all know if we increase the money supply, then probably going to see prices go up, right? If there's a monetary policy shock, prices should be expected to go up. So prices would go up. Well, if there's an increase to some monetary aggregate, that monetary aggregate has to increase, right? So here it's the money base. And so the money base is going to increase. Now, if the money base increases, I would expect the interest rate to fall. So I get an increase in money, a reduction in the interest rate, and then an increase in prices. And then I go, what does GDP do based on that? So I get all these shocks where I have an increase in money, a reduction in the 10-year treasury yield, and an increase in core PCE prices. And then because I'm not just pulling like, one from here, one from here, one from here, it's if I've got a set of shocks where three of those, right, prices, money base, and the treasury yield move in the direction I want them to, I'm going to pull all of them, and I'm going to look at what the response for real GDP is. So, I guess I got a little ahead of myself here. Let's think about what a monetary policy shock is. So the central bank increases the money base. When they increase the money base, interest rates fall, right? The cost of borrowing falls. So the cost of borrowing falls, well, the interest rate would fall, and people want to borrow more. That increases the money supply. So you get more money entering circulation. People are demanding more stuff because they've got more money in their hands. So companies have to make more things. Now, prices are generally a little slow to adjust to demand shocks. Thus, if prices can't fully adjust immediately, output has to increase. And as output increases, then firms will begin to raise their prices a little bit more because, well, it's still in response to a demand shock. So what you would expect to see is an increase in M, or the money base, a reduction in the nominal interest rate, R, an increase in prices, P, and then presumably there'd be an increase in output as well. But, maybe that's a little uncertain. We don't know if output's going to go up or down. Well, actually, we can look at this and say, hey, output probably increased. So what are we looking at? Well, these are a set of impulse responses for the four variables that I was estimating. I got the increase in the money base. So this is where the shock really occurs. Okay, so I get a little bit more than a 1% increase in the money base. From that, well, the interest rate falls, right? The 10-year treasury yield here falls. Now the reason I'm using the 10-year treasury, we'll get into when we learn about the financial crisis. But during a vast majority of this time sample that I'm looking at, the central bank really shifted its attention from the federal funds rate, which was locked at zero, couldn't go below zero, to a longer-term interest rate. Now, since we just learned about the term structure of interest rates, you probably go, okay, well, yeah, that sort of makes sense because, we're going to go out along the yield curve. The idea here was instead of getting the Fed funds rate lower, they wanted to flatten the yield curve, or like the relative prices of borrowing from across different time horizons. So if you lower the 10-year treasury yield, then you lower everything of maturity less than 10 years as well. So we see a reduction in the 10-year treasury yield, an increase in consumer prices, and then from that, you also see an increase in real GDP. And it's an increase in real GDP. I guess I went from the green to red now for the median draw, but the median draw is really what we're looking at. And so initially it kind of increases, right? And then, well, it's a little bit bigger over here. So where's the maximum response? Well, I'd say really the maximum response is at 35 months. Okay, so at 35 months, it's 0.06% above its steady state, or where it was just going along a flat line prior to the shock. Core PCE prices, where's the maximum response? Well, the maximum response is right about here. What is that? Well, 0.028. Screw it, round up to 0.03. So 0.03%. And we get like a 10 basis point drop in the 10-year treasury yield. So that's kind of how you'd interpret this stuff. Okay, this goes up by this amount. This goes up by this amount. This drops by this amount. That's how we would want to interpret these things. So it looks like everything kind of moved as we thought it would. Now, this is really an interesting question for us to ask. What about all that monetary neutrality stuff that we learned at the beginning of the semester, right, in the quantity theory of money? And good question to ask, because if I'm teaching that stuff to you, and I'm teaching you about monetary neutrality, wouldn't I want to, actually think maybe we could observe that in the data? Because if it's not something you're observing, what's the point in teaching it? So we should theoretically be seeing that in the impulse responses. And the interesting thing is we actually do. So remember, if there's an increase in the money supply, a one-time increase in the money supply, in the long run, there would be responses in only nominal variables, not real ones. So you'd see prices move up like a lot and output not really move up so much anymore. So if you take another set of impulse responses and look at them over, say, a 60-month horizon instead of a 36-month horizon, you'd end up seeing something like this. Okay, well, it was a different run that I made, so the run isn't the same here. Here's the interesting thing. Real GDP increases above its steady state. This is kind of where I was like, you don't always just want to look at the maximum response. Generally, you do, but it kind of flattens out, right? There's no real change above the steady state anymore. And then, interestingly enough, you can see these bands here. This band is getting closer and closer and closer to zero. Eventually, it does cross zero, and there's no longer significant change in real GDP. Now, this the only real variable that we're looking at here is just real GDP. It flattens out. So it kind of does tell us if there's a one-time increase in the money supply, eventually it has no effect on real economic variables. So monetary neutrality does kind of hold here. It takes a while before it kicks in, but that also makes sense. If you remember the whole thing from Milton Friedman about monetary policy operating with long and variable lags, boom, here it is. So the quantity theory of money does hold. It's just not immediate. There's short to medium run considerations and then like medium to long run considerations. Different things can have different effects across different time horizons. If you get a couple slugs in NyQuil right now, you probably start to feel it in a few minutes and it lasts for a couple hours. But a week from now, assuming you don't have any more NyQuil, you won't be feeling it anymore. All right? You probably won't even be feeling it after tomorrow morning. So, okay, NyQuil has an effect in the short run, but in the long run, it doesn't. So long as you don't keep taking it. If you keep taking it, those pink and purple elephants are always going to be sitting in the corner and they're going to be looking at you weird. But if you eventually stop taking it, they eventually go away. That's kind of the idea here. If you have a one-time slug of NyQuil, you'll feel it in the short run, but in the long run, you won't because it doesn't stick with you forever. Now, that's the end of this lecture. So I guess it ended up being a little bit longer than I thought it was going to be. Now, there's a lot more that we'll cover, but it comes in due time. The next chapter uses some VAR modeling in one part. So I really wanted you guys to see what a lot of the stuff was before we moved on to that chapter. So as the course progresses, we're going to be doing more with these impulse response functions. And again, all you really have to do is just look at them and interpret them. And it'll be like, hey, what kind of a shock is this? Well, if your theory tells you this goes up, this goes up, this goes down, you can just say, okay, well, does the theory for like the signed responses here match up with the combination of signed responses I'm seeing in these little graphs? And if it does, well then, hey, there you go. Boom, we're good. So yeah, that wraps everything up here. Thanks for watching, and I will be making more videos in the future. So peace out.